The basic idea for the bisection algorithm is best illustrated by an interactive demo and hopefully by watching this video. Recall that we use widgets to create the interactivity. Widgets are very useful for illustrating concepts and exploring ideas. So we're going to, from the IPyWidgets, import the usual things I like to import, which are interact, interactive, fixed, and interact manual, and then just import IPyWidgets all together as widgets. So I like to run that code cell, and here's a suggested activity. If you really want to understand things, do the following. Update the docstring in this compute bisection function to describe 1, the role of the various parameters, and 2, what variables, if any, the function returns, and add at least one doc test. So if we look at this function, and I see I already have this docstring, this simple function applies up to n iterations of the bisection algorithm, you see that it needs a function f in order to run, just like we needed a function f to instantiate the myFunctions class that we were seeing above. We then need to give it an a and a b value, where a is supposed to be less than b, and it defines an interval where we look for the root of the function between a and b. N is the number of iterations of the algorithm, and then we have some tolerances. If our interval becomes smaller than 10 to the negative fifth, we stop. If the function values get within 10 to the negative eighth of 0, we stop. Those are things that just remove us from this algorithm. The reason we have these tolerances is because we have a while loop in here, and we don't want to necessarily have infinite loops, so that's why we say, okay, there's a max number of iterations, which is n, that's why I said it's up to n iterations. It doesn't necessarily take n iterations to reach these tolerances. So we don't necessarily even want to take n iterations if we reach these tolerances. So basically we have this while loop. It won't go more than n times because we have this iteration counter that we immediately start adding 1 to every time we iterate through the algorithm. We have some checks here that if a is greater than or equal to b, we raise a value error and we return this message that the bisection algorithm requires a to be less than b. And then if f of a and f of b are the same sign, so if you multiply them and they're positive, then they're either both positive or both negative. And they need to be of different signs in order for the bisection algorithm to work. So that's just the start. Let me actually jump to the Wikipedia page now, and let's look at this figure. This figure illustrates what's going on with the bisection algorithm. You would start with an initial a and b, and you would have function values that are of different signs. In this case, f of a1 and f of b1, your first guesses of where the root could be between those values. You have f of a1 is positive, f of b1 is negative. But you could have this the other way around. The f of a doesn't have to be positive. It could have been negative. F of b would have to be positive. The idea is if there are different signs and the function is continuous, well, the only way it could go from positive to negative if it was 0 somewhere between these two values. Again, the function has to be continuous. So then you would start iterating by cutting the interval in half, bisecting the interval. And so here you look at this and say, okay, well, if I divide this in half, that would be this point basically right here, right in the middle. And then you evaluate the function, you see, oh, it's negative again. So if it's negative, well, which of these endpoints was negative? It was the b1. So it's going to replace the one that was negative and said this will be b2, and a1 basically stays here because it didn't move at all. So now your new interval is half the length of the previous one. And you could guess, well, I'm going to guess that where it crosses 0 is between these 2 points. And so then you'd cut that interval in half. You'd put a point right here. You call it C as your next best guess. But if you evaluate the function, you'd say, oh, it's positive. Well, f of a1 was positive. So I'm going to replace a1 with a2. So now my third interval now has a2 and b2. And now it's 1/4 the original size. Just 2 iterations, and I've cut my interval in one. It's 1/4 the size. It's 25% the length of the original interval. And now I'm going to guess again in the middle. I'm going to get this new point that's going to be right here. That's going to be my third guess at what the root is. And when I go to evaluate the function, I see it's positive. So then that becomes the new left endpoint in this case yet again. And then you start again seeing that where the root is in this big red dot, you're already by 3 iterations getting a really good guess as to where that is. You're pretty close. It would probably be right around where my cursor is right now on the screen, which might be a little hard to see. So that's the basic idea of the bisection algorithm. So I'm checking to make sure that the conditions hold initially to even do it. And then if those conditions hold, we perform the bisection algorithm. So the first thing we do is we pick a C that's the midpoint of a and b. So I just average them. If you add a and b together and divide by 2, that's the midpoint. Then I check to see if c is an approximate root. So I check to see if the absolute value of f of c is less than that tolerance value here. If it's within 10 to the negative 8 of 0, I'm going to be like, that's close enough to 0. And then I would just break out of the while loop. If that didn't happen, then I need to determine, well, should a or b be replaced by c? And it's just determined by the sign. If f of a and f of c have different signs, then that means b should be the new c. So right, if f of a and f of c have different signs and f of a was different than f of b, that means f of c has the same sign as f of b. I know that might sound very, very weird, but if you go through the logic, I was just hearing myself say it out loud. If you go through the logic of this, it's exactly doing what I was saying is going on here, where you want to replace the left or right endpoint from your previous interval with based on the sign. So if where you did the bisection, if it has the same sign as one of these points, that's the one it should replace. So you say, okay, well, in that case, if f of a and f of c have different signs, then f of c must have the same sign as f of b, which means my right endpoint should become it should be replaced by the c value. Otherwise, the left endpoint should be replaced by the c value, which means either way, my new interval is either a to c or it's c to b based on my previous c, but that c was at the midpoint, so I've cut my interval in half. And then I just keep repeating this. Unless the new interval I've created is too small. It's smaller than the interval I care to look for. If it's within 10 to the negative 5th, you go, geez, no matter what, I already have an estimate of this root to 4 digits of precision, at least, as soon as this interval is less than 10 to the negative 5th. So you would just break out of that. And then I return the final interval values, a and b, as well as c. So that returns a tuple. And all that information might be stuff you want to put inside of this docstring a little bit as a suggested activity. But let's just go ahead now and run that. So again, I want to point out kind of this is the whole bisection algorithm. Just bisect the interval in half and then replace endpoints. Everything else is just a check relative to, like, is it close enough to 0, or do I have enough digits of precision that I don't care to try to improve this any further, or I've just reached the max number of iterations that I care to perform. So all this other code around it is just in some sense peripheral, and it's to control the amount of effort I put into searching for C. But the actual way the bisection algorithm works is that computation and this computation. So line 21 and lines 28 through 31. That's the real part of the algorithm, and everything else is just a control of how long I spend in the algorithm. All right, now let's actually compute A, B, and C, where I'll bisect this F. What is the F even at this point in the curve? I don't know what I think it's still that function, it's still that the original third order polynomial. That's exactly what it is. It's that original third order polynomial where the approximate root was 1.521. And you'll see it's 1.521. So if you go back, this is how I defined that. I started with that function. I ran this, I saw, okay, 1.521, and then I went to the top of the notebook and I coded up 1.521 as the approximate root. And so I was doing the bisection algorithm between 0 and 2, and this was with the default of 10. This used the default 10 maximum iterations as well as these tolerances. And so I can also return the tuples of outputs as a single variable. So here I parse them out as A, B, and C. I can return it all as bisect results, just if you want to see that the output is a tuple. The length of the tuple will be 3, and then the last component is what I want, and I can use negative indexing there to get the approximate root. So you can see it's a tuple, there's 3 things in that tuple, and again, the last one is the approximate root. You could just ignore all the values other than C by using underscores. I'm just showing you some new ways to interact with a function that can return several outputs, but maybe you only care about one of them. So you can do something like this where you use an underscore, basically, so it's just like your shift hyphen key, and it just creates an underscore. You do underscore, comma, you have your C, and then you say compute bisection. That'll do the same thing. Now I just have C, and it didn't assign those other outputs to anything. What about, I might have assigned them to, actually now I'm a little curious, did it assign them to underscore? It did. So that is actually that's this one. It will be whatever the last one is. So it's just kind of like some throwaway variable. It's not that it doesn't assign it to anything. They just get assigned to underscore and underscore and underscore. So whatever the last underscore assignment was from there. Okay, it's a worthless variable name though. Underscore. What are you going to use that for? Maybe the cleanest way for you to do it is just to actually say, well, the output is itself a tuple, and so I'm calling the function, but then maybe I only want the last argument. I know there's 3 of them, and Python indexing is by 0, so I can do that with the square brackets with 2, and that's another way to get the C value out of that function, the approximate root. Or you could use the negative indexing. So I'm just trying to show you things that are, again, connecting to previous ways you've seen involving indexing and how to get the output of the function that maybe you really care about. And if you don't care about the final interval, you just want the approximate root C, then all the things I was just showing you are reasonable ways about how you might go about doing that. Now let's add some interactivity. But first, let's just take a little break. I think you should pause the video and maybe play around with this function with things that are not the default values and see what other inputs you get, and just make sure you understand it. All right, now we're going to add some interactivity. Watch what happens if you choose B or A such that f of B and f of A have the same sign. But how do we know when that will happen? Here's a hint. Refer to the plot. So I want to use the interact function. I could also do interact manual, but I'm just going to use the interact function on the compute bisection algorithm. I'm going to fix the function f. I want A and B and n to all be sliders that I move. I want the A and B to be float sliders. N should be an int slider because that controls the maximum number of iterations, so it should be an integer. And then my tolerances I will just go ahead and fix as the default values as well. So when I run this, and now I see I have A and B and N that I can all play with. And when I start to move this around, let's say, and you can see this, here's the output of the function right here, as that tuple. So if you can see that the final C value that I got was the B value here, because just at that point it didn't compute based on the algorithm. So you can see, I think it breaks out. So it does this, and eventually, it got to that tolerance very quickly, and it just broke, and which meant like the B at this point was equal to the C because it did it from the right. Doesn't really matter that they're the same. That's my main point. So you can shrink this down a little bit, and eventually get it to see that it's something different. Like here, it's equal to the A value, just because that's what happened. A was assigned to be C. And then then the interval was too small, and it like broke out of the loop. Or at least that's what, or maybe that was just at the final interval, because we're always assigning A or B to be C before we potentially break out. Except tolerance is reached. Few minor points here. Anyways, let's just start moving A and B around though. Let's say I take A and I move it closer to B. That's just a little, and I'll make B, let's say, there we go. Notice it doesn't matter the positions of the slides, like A is 1 and B is 1.5. It looks like A is to the right of B, but you have to pay attention to the value here. So A is a float slider that goes it starts at 0, but it can go from -1 to 2, whereas B starts at 2, but it can go from 0 to 3. So the leftmost value of B is still to the right of the leftmost value of A, but I can cross them visually even though B can still be larger than A. That's just because the sliders are the same sizes. So just keep that in mind, that I didn't make A greater than B. A is still 1, B is 1.5, but look at this error. It says it's a value error. The bisect algorithm requires f of A and f of B are different signs. I should say to be different signs. Requires these to be different signs. I like that better. It seems weird to say are different signs. Let's run that again. Make my error message not so ugly. So I'll make A be 1 or 1.1. It doesn't really matter. Here we go, like 1.5. There we go. It says that's the problem. These are to be different signs. The bisection algorithm requires f of A and f of B to be different signs. So this is exactly the value error that we raised. This is what's happening. It's not even doing one iteration. And so the algorithm's actually, the function's running as it should when this error has occurred. Because the algorithm's not even supposed to run if these have the same sign. It can't even work. It needs them to be different signs. So what's going on, right? How do you see that and make sense of it? You have to plot the function. We can easily play with other lambda functions, by the way, to see this, like that this error can occur. So if I do this here, this is a function Here's a lambda function that I'm passing right to the compute bisection. Everything else I kept, I believe, the same in terms of a goes from -1 to 2, b goes from 0 to 3, and the other things are fixed except the function's changed. It's a lambda function passed directly to compute bisection for the f parameter. I'm just passing it this, I'm fixing it as this one lambda function, and that one lambda function is sine of x cubed minus x minus 2. So it's that polynomial, but I'm using it as the argument of a sine function so that it adds some oscillations. And right away at the 0 and 2, the default values for a and b, which were fine up here. If I move a back down to 0, and I move b back up to 2, you're going to see the errors disappear at some point. Like, that was fine here, but it's not fine here. And you start to say, like, gosh, you know, I can get all these different errors, and yeah, it's telling me that they need to be different signs, but how am I supposed to know what good reasonable values are to even start for a and b? Well, you need to plot the functions to really see what's going on. So the suggested activity here is, after looking at the plots below, or after making your own, enter in more reasonable values for a and b in the widgets above to see the different routes we could approximate, as long as we did use suitable initial values for a and b. So I'm speaking specifically to the sine function. So here I'm going to create this new fancy function with this lambda sine of x cubed minus x minus 2 as the argument of the sine function. So this is from the my functions, and these create some fancy functions. And what are they useful for? Well, it has a plot method attached to it, and I can give it an x-min and an x-max of 0 and 2. And when I do that, I go, well, geez, it passed 0 there, but when b was 2 and a was 0, you see, oh, they're both negative. They're both negative. Whereas the original, this other function, if I can scroll up for just a second, there it is. Here's this other function kind of between 0 and 2. You can see that it was positive and then negative over here at 0 and positive here at the right. That was the original cubic function we were looking at. But when we put that cubic function into the argument of sine, the function behavior changes quite a bit. In fact, it has 2 roots in this interval. But we can't apply the bisection algorithm unless we give it an a and a b value that are different. You could see, oh, the b value maybe needs to be something like 1.75. You know, it looks like it's still around 1.512. In fact, because sine of 0 is 0, it should have the same root, but it has this new root as well. Let's actually look between 1.25 and 1.75, because you can just kind of zoom in. This is, again, using that same function, but this is a nice thing about having this plot routine attached to it, is you can just quickly say, okay, let me plot it with a new x-min and a new x-max and try to zero in on where I think the root is. You go, you know what? Those look like some decent values that I could try to find a root for. So maybe I should choose 1.25 as the a and 1.75 as the b and see if I can estimate the root. But you'd also had this other root that seemed to be over here, and we see, oh, well, at 1.75 it was positive, so maybe I should look at 1.75 to 2, and that's another place I could try to find a root. And then I could try to set the root, and I could find these estimates of the roots. I could then take the function, set the root to be these different values, and create different annotated plots for where these different roots are that are zoomed in at different positions, given different x-min and x-max values in the plot method for it. So just having this as a class, as an object, really allows you to explore where the potential roots are, then use an algorithm that's designed to find the roots, and just go to town. Start creating the visuals and have a lot more of the storytelling aspect with your functions and how you're presenting material, because you're able to use everything in a really integrated manner and kind of hide a lot of the complexity of the code inside of the methods and data attributes of the function. Now let's actually plot a different function that never crosses the x-axis. So I'm going to create this newer function, and it's x to the fourth minus 2x cubed plus x plus 1. This is I'm going to make it fancier. So this is my newer function. I'm going to make it fancier with my class. I'm going to plot it from -2 to 3. Excuse me. And if you look at this, you say, oh, look at it. It always stays above the x-axis. It has that little bit of a wiggle that you often see with a generic fourth order polynomial, but it never crosses the x-axis. So in this case, we hope to get, in fact, we better get an error when we try to find a root to the function above. In fact, we cannot find a root. This has no roots. It never crosses the x-axis. It's an even order polynomial. It doesn't have to cross the x-axis. Just like you might remember that the roots of a quadratic, based on the quadratic formula for a second order polynomial, are sometimes complex valued, meaning that there are no real roots to some polynomials. So the key points here is the compute bisection algorithm that we've coded up, it is working properly if it gives us an error in this case. If it gives us an error in a case where we try to solve for a root where no root exists, or at least where the bisection algorithm can't be applied. In general, an error produced by a code does not mean that there is an error in the code. Many times the code is operating as expected or at least as intended. Many errors are user errors, where the user tries to use the code in a way that it is not intended to be used, which causes an unexpected error. We're actually expecting and looking for these potential issues and returning that information to the user in an informative way, which is related to the try and accept command stuff that I had you do and doc test that I had you work on back in homework 3. When an error is returned by the code that it is written to catch, such as the compute bisection algorithm is, then this is an expected error that the programmer knows either through domain-specific knowledge or by testing code with users and gathering feedback, perhaps in like a beta testing, may happen. So they know this may happen, and they want to give that information to the user. That, hey, I can't solve this problem for some reasons that hopefully the user finds useful. So again, I'm just going to show this here. This is with that fourth order polynomial. And there are no A or B values you can possibly choose here that will not produce this value error. They will all do it. Whereas if you go up here with this one with the sign function, we saw if we make A like 1.2 and B to be like 1.7, now we can estimate the error again. We see it's like 1.521. But if we made A up to like 1.7, and we made B to be 2, now we're estimating where that other root is, which are things that you can play with. And the errors went away. The errors we were getting are the errors we were supposed to get. That's the important thing there. So scrolling back down, what is the bigger lesson here? Plots are really useful, and we should often do some initial, call it grunt work, on examining the problem we are asked to solve to make sure that we actually set it up correctly or that it actually even has a solution like we think it might. The compute bisection algorithm we saw above, relating what we're seeing right here, was not failing just because it output errors. It was functioning again just as it should. We gave it bad choices of A and B as the default values in the widget. Simply looking at the plot reveals this to us right away. While we might not always be able to plot a function for many reasons, such as, here's some examples. For example, it takes too long to evaluate the hundreds to thousands of times necessary to make a reasonable looking plot. The dimension of the input space could simply be too high to properly visualize. There's other reasons that I'm not listing here. You should always try to visualize the data somehow, associated with whatever problem you're solving, and in some way in order to orient yourselves properly on the problem. Failure to do so can lead to a lot of frustration because a lot of people get very frustrated when they start seeing errors in code and they say, why isn't this working? I coded the algorithm correctly, or I'm using the functions the way they said they should, but maybe I'm not giving it inputs or a problem to solve that it can solve. And that's where data visualization, and again, this idea of some of the data visualization as a precursor to the data storytelling you might do, is really important. And that's why I think I'm just harping so much here on the plotting of the function, why I started with the visualization of the function, the annotations, is that this is just a bigger lesson than just this notebook, just root finding functions. This is a really important lesson to carry through everything in data science and in computational science, is visualizations are worth so much in terms of intuition and setting up the problem correctly that you really want to take the time to invest in proper visualization tools and investigation of the visuals that you have.